Hello everyone, welcome back to another class on regeneration biology. In today's class, we will learn about the importance of scaffolds. We have seen different types of scaffolds. We have seen decellularized scaffolds, ECM, etc. And we will try to understand how it is important, and especially having said that decellularized ECM is best many times on various biological or clinical scenario. We have to use artificial scaffolds because they are the one which is easily available. They are the one which is you can get it on however large quantity or to however or whatever number of people, etc. So we cannot rule out the advantages of artificial scaffolds, and we will learn what is the importance of scaffolds and how they are defined, etc. So here is an outline. What are biomaterials? Some questions we can ask. What is the need to know them? Why we need to know them? Scope of biomaterials and scaffolds, and the types of scaffolds used in tissue engineering, and desirable properties of scaffolds for tissue engineering. What are the desirable qualities a scaffold should have? And what are the advances in biomaterials and scaffold technology that we have achieved? And what are some of the challenges which we face with the scaffold? So these are all things which we try to address. And a few books are listed here, suggested books for understanding more about the scaffolds: the biomaterials and tissue engineering applications, a review of the past and future trends, one book, and biomaterials and introduction, another book, and biomaterials and tissue engineering, another book. And the author's name are listed here. And there are many more books which is available to read. If you want to gain in-depth knowledge about the subject, you should read as many textbooks as possible, or as many scientific articles, review papers. You should read it so that you will know too much about the subject, or adequate information about the subject. You can get it through these approaches. So scaffold, the concept and the functions. By definition, it is a synthetic support material used to replace a part of living system or a function in contact, or it can do its job by staying, or its performance is by staying in contact with the living tissue. Say for example, if you have a cardiac valve issue, so the ideal thing is you should have the exact muscular cardiac valve. Many times it's not possible, so you can artificially put a cardiac valve which is made of non-biological material. It's made of plastic or other polymers, etc., but it functions in conjunction with the heart. It's not that the heart rejects it or your immune system rejects it or something. So that biomaterial is so friendly that it will not create any trouble whatsoever, and it does the job just like any other normal cardiac valve. And so in that scenario, you don't need the real heart valve, because even if you could not put a biological heart valve, the heart function is just the same. So in that situation, many biological materials can perform the duty without any drawbacks whatsoever. So this is what we should keep in mind. Not that if you have to have a biomaterials or a regenerative approach or a fixing approach to be made, they have to come through only a living tissue. Not like that. There are other scenario. Say for example, if someone need a support to their bone, the center portion can be a polymer or an iron rod. That is okay, as long as it doesn't give any trouble, as long as it doesn't affect that person's motility, movement or functioning. It is okay. It is not a bad thing to have. We cannot insist, no, I want a bone itself inside, which should have a bone marrow also, so and it should produce the blood also inside that bone marrow. One don't need to unless it is going to be life threatening. So this idea also we should get it while learning about tissue engineering and biomaterials. So materials of used for biomedical applications are often coming under this biomaterial category. And there are scaffolds and various 3D platforms used for tissue engineering, and it is used clinically or experimentally in implantable electronic devices, drug delivery systems, hybrid artificial organs, bone substitutes, ligaments, and tendon replacements, etc. So biomaterials can function in so many other uh, part as it is, which is outside what is mentioned here. Some of the major ones are mentioned here. So roles of engineered scaffold. How engineered scaffolds contribute and function. They allow cell attachment and migration because it should be friendly to the cell so that it can attach and migrate and deliver and retain cells and biochemical factors and enable diffusion of vital cell nutrients and expressed products. These are minimum required qualities of a scaffold and exert certain mechanical and biological influences to modify the behavior of the cell phase, which phase of the cycle or phase of that cell it is being, whether it's in a reprogrammed phase, proliferating phase, or in a differentiated phase, etc. It should support based on your demand. If you push a cell into a differentiation phase, the scaffold should support it. It should not stop it. So these are all the ideas one should keep in mind when you are engineering a scaffold. Now let us see some examples of scaffolds application, or some we have already seen it. A long list is mentioned here. Orthopedic tissue constructs and grafts, neural tissue regeneration, scaffolds are used especially for spinal cord injury. Skeletal muscle regeneration, scaffolds are used. Joint replacements, hip replacement or the knee replacement, etc. Bone plates, especially the patella bone, or where you have lost a larger portion of the bone in an accident or some other situation, you can replace joints or bone plates, etc. And bone cement, biomaterials are used to cement the bones. Hip joint, artificial ligaments and tendons, dental implants for tooth fixation, blood vessel prosthesis, like you can have a blood capillary which is made out of a biomaterial, heart valves, skin repair devices, cochlear replacements, contact lenses. Many of you would have used contact lenses, which is a good example of biomaterial because it works along with your cornea, which has got correction, refractive correction, and you don't need to use your glass for reading or vision purpose. So it's a very good example of biomaterials in a widely used very good example. What I mean is, majority of the people who use a glass may have come across the applications of a contact lens. What are the desirable scaffold properties? Having said that, scaffolds are important, needed, etc. What are the properties we should have? We can start from anywhere. Let us start from here. Biodegradability. Biodegradable means once, based on the location of delivery, once it is put in, the scaffold should get degraded. Some good example you can see, absorbable suture. You would have heard about it. Like if a C-section delivery happens, then doctor will make a cut in the belly and also in the uterus. So then only they can access the baby. Once the baby is accessed, then they will put a suture inside also, but that will be an absorbable switch. But what you put in the belly need not be an absorbable switch because it will be a removable switch, ligature, absorbable suture and non-absorbable suture, ligature, you can put it. And these days people use glues also inside. So understand whether you use a glue for ligation or absorbable suture cord thread, they all have to be biodegradable. You don't want that glue or a suture ligature staying there for rest of the life. That can create lots of unwanted trouble. So biodegradability means it should stay for say 1 week or so, then it should disappear. By then the wound is healed. Then why you need a ligature present there? And then porosity, it should allow the migration of nutrients, oxygen, etc. So it should be porous. Porosity means it's like a sponge. Sponge has got lots of holes. And mechanical requirements means it should be strong, tough, etc. You don't want a ligature, when you are suturing, it is breaking. Very good material, absorbable, biodegradable, but tuck, it is breaking. So you want to have good mechanical requirement. And moldability and sterilization. You should be able to make it to any shape and mold, whatever shape you want for this biomaterial. It should be able to, and also it should be amenable for sterilization. If you sterilize either by autoclaving or UV radiation, if it deforms, then it's not a good biomaterial. And cell adhesion and proliferation and differentiation. It should support. Cells should feel friendly to this biomaterial so that it doesn't elicit an unwanted immune reaction or cells feel uneasy, unhappy, etc. And transport requirement. It should allow the nutrition will pass very beautifully through this biomaterial. And biofactor delivery, that you will be able to give any growth factor or any other favorable growth favoring molecules into the cells through this biomaterial. And surface chemistry. The surface chemistry should be such that the surface should feel okay to that of a typical extracellular matrix, or the cells should be able to interact with this biomaterial as good as what a cell will do to its immediate extracellular matrix. And biocompatibility. It should happen that it is compatible with me but not with my friend. It should not be that person specific or something. It should be compatible with every tissue and every organ. Then only it will become a beautiful biomaterial that can be used for making scaffold. Suitable properties of scaffold. They have chemical properties, physical property, and biological property. Chemical properties, they should be biologically active and sterilizable. Biologically active, what it means is it is friendly to the cells. And sterilizable means you don't want any unwanted pathogens or bacteria or fungus or mycoplasma to grow. So you should be able to sterilize before inoculating those scaffolds with the cells. And physical property, mechanically supportive. If everything is fine, but the moment cells are growing, it is crumbling because the weight of the cell, or the moment you pass the nutrition or the medium flowing through them, then they are perishing. You don't want those kind of scaffolds. And biological property should include biocompatible and biodegradable. This I already discussed in the previous slide, that it should be friendly to a living cell that is growing on it. And let us look into the chemical properties. Chemical properties in detail include suitable surface chemistry or bioactivity for cell attachment. If the cells are not able to attach on them, then that scaffold is not of too much good quality. To facilitate binding of the biomaterial with the cell surface receptor. Every cell has got different receptors. Some are used for attaching onto the matrix. So the same receptor, a cell should be able to use it to bind onto the scaffold also. In case of synthetic polymers, if they lack suitable surface chemistry, then their surface modification has to be performed. Scaffold is good, tough, very friendly, but it is not welcoming cells. So you can do some coating so that now the cells will find home. So this logic also you should keep in mind. So that biomaterial should be allowing surface modification. That modification is now going to be helpful for the cells. In case of synthetic polymers, if they lack suitable surface chemistry, then their surface modification has to be performed. For example, RGD, that is arginyl glycyl aspartic acid. It's a 3 amino acid peptide, arginine, glycine and aspartic acid together. It's a small peptide. Inclusion for better cell attachment. So when you make the biomaterial, you include this also, RGD, arginyl glycyl aspartic acid, so that biomaterial is now more friendly to the cells because it will interact with this 3 amino acid peptide. Sterilizable without any property loss. So you made everything fine, but after sterilizing, either with UV or maybe gamma radiation or autoclaving, it lost its property. You don't want that. So to prevent contamination, you must sterilize the biomaterial, but it should retain its quality. And let us look into the physical property. It is little bit of physics comes into picture, mechanical strength, that it would withstand shear stress generated by biological fluid flow, like I mentioned. So stress and strain, this is the graph. When you, like, the force you apply and the body change that is occurring. So the stress is the change that occurs. If you apply stress onto a elastic, then its body deforms, it becomes longer. So stress and strain has got a connection until it reaches an elastic limit. You also know, and rubber band you can stretch up to certain limit and it will not go exponentially long. After that it will not stretch anymore, and if you stretch anymore it will break. So elastic limit to the break point, there is a slight change in the shape. Once you continue to apply strain, the change in shape will not happen, and after that there will be a break point where it will lose its the so-called elastic property. And types of forces that can be applied to the scaffold, different types of forces are applied to test it whether the scaffold is good or not. Tensile force, a force tending to tear it apart, like you take a paper and try to tear it, that is the tensile strength. Then compressive strength, a force that squeezes an object surface together to cause its mass to bulge. You're pressing something, you take something and try to press it, how much force it can take it. And then shearing force are unaligned forces pushing one part of the body in one direction and another part of the body is in the opposite direction. And it's different from tensile stress. This one, shear stress, is like, you are twisting something, that is shear stress. You are it's not just uniform, it's like a multi, like you take a cloth and you twist it, that is shear stress. And then comes the torsion stress. Torsion stress is the winding force on an object. That means one side of the object is pushed in one direction and the other side is pushed in the opposite direction. So a torque force when you apply, so it should be able to withstand it. You don't want the body to or the scaffold to keep breaking when any of these forces are applied. And terminology, let us need a little bit more. Stress is an applied force or a system of forces that tends to strain or deform the body. So stress is the force, strain is the change in the body. Strain is a change in the dimension of the body under a load. Like elastic, 1 inch elastic or 1 inch rubber band, you pulled into 10-inch rubber band. So 10 is the new shape. And why it became 10 inch long? Because of the force you apply, and that force is the stress. And change in the dimension of and once you leave the stress, it will come back to the original dimension. It may be the ratio of lengths, areas or volumes, thus it is dimensionless. The strain is dimensionless. It gives the extent to which a body is distorted when it is subjected to deforming force when it is under stress. And the load is the weight divided by force applied. That is the load which you describe in the physical terminology. And elastic limit is the stress that can be applied to an elastic body without causing permanent deformation. The stress point at which a material will no longer return to its original shape, it is subjected to a higher stress. So that is, once it is an elastic limit, it will not come back. You may have seen it, once you put an elastic around a box for 1 year and you try to take out, that elastic will no more come back to the small shape. It will remain longer. So brittle materials tend to break at a shortly past their elastic limit, while tactile materials deform at a stress material beyond their elastic limit. If a good rubber band is there, even if it is reached elastic limit, it will not break. It will stay there, but it may not come back to its original shape. So like 1 inch rubber band, I pulled it to 10 inch and multiple times. Now it will not come back to the 1 inch every time. It may now stay in 1.5 inch because of multiple pushing. Break point is a point of discontinuity, a change or cessation. That means it is not going to come back to the original shape at all. It broke into two pieces. Yield point is a terminology used, the point in the stress strain curve at which the curve level off at the plastic deformation begins to occur. So this is the yield point in which we should understand the stress strain curve. The curve levels off, they just weigh normally. So these are all some terminology you should keep in mind. Yield stress, the yield strength or the yield point of the material is defining in engineering material science as the stress at which a material begins to deform plastically. So this is the yield stress, the terminology which is used to explain the ability of the biomaterials to deform plastically. Prior to the yield point, the material will deform elastically and will return to its original shape when the applied stress is removed. So this is a good property for a biomaterial to have. Once the yield point is passed, some fraction of the deformation will be permanent and non-reversible. Like I gave an example of the rubber band. If you stretch multiple times 1-inch rubber band, after multiple stress, it will no longer will come back to 1-inch rubber band. Once you remove the force, it will stay 1.5 or 2-inch. Young's modulus, the slope of the elastic portion of the stress strain curve in a quantity often used to assess a material's stiffness. So then comes in the mechanical property the ultimate strength, that is the maximum value of load bearing at which it may get permanently deformed. That is what the ultimate strength. And tensile strength, the load bearing up to which a scaffold could be elongated prior to breaking. So it is tested for several fibrous materials. And then compressive strength is the degree of compression tested for a porous scaffold. If it is having pores, a sponge, you think about it, you are pressing it and you don't want to reach a stage where all the pores are closed. If it is allowing the closing of the pores, then there is a chance when the fluid force comes strongly, then the pores may get clogged. So even while pressing, the pores should not reach a stage where it completely closes it. And also suitable Taylor properties like pore size, percentage of porosity, etc. also has to be taken into consideration. Now, if you look into the biological properties, biocompatible, we have discussed it, that is basically the ability of a material to elicit an appropriate biological response in a specific application by not producing toxic, injurious or immunological response in a living tissue. If any of this happens, say you get inflammation because of the cells are interacting, because the biomaterial is somehow attracting immune cells and you get inflamed, and that is bad for that tissue and maybe for rest of the organ. And you don't want to have any toxins present in these biomaterials. So that is why biocompatibility comes into picture. Biodegradable, that means the rate of scaffold degradation is equal to rate of tissue formation, because when a tissue is being formed, then that tissue is secreting its ECM also. No tissue need to be told, okay, secrete ECM. That is their normal behavior. And when that is being produced, you don't want this biomaterial again. So it should coincide. If 1 gram of ECM is produced, 1 gram of degradation of the biomaterial should happen, so that there will be an equilibrium between them. So if you look the scaffolds, different qualities has to be taken care of. That is the polymers. They are ocular implants, drug delivery devices, skin cartilages, several polymers are used. Ceramics bioscaffolds, what they use is they are used for bone replacements, heart valves, dental implants, etc. Semiconductor materials, they are used for implantable microelectrodes, biosensors, etc. Metals are used for dental implants, orthopedic screws, fixation, etc. So they are all coming under scaffold, but they are different chemical properties they have. So some examples of scaffold materials are listed here. The polymer type is been given here. Silicone rubber, the material is Dacron, polymethyl acrylate, polyurethanes, hydrogels, cellulose, collagen, silk fibroin, chitosan, gelatin, alginate, etc. are polymer examples. And they are used for application in catheters, tubing, vascular grafts, intraocular lenses, bone cement, catheters, and pacemaker leads. So you can read, the list continues, many are there. And metals include stainless steel, titanium, alumina. They are used as metal examples. They are mainly used for orthopedic devices, stents, orthopedic and dental devices, etc. Ceramics include bioactive glass, mainly silica, hydroxyapatite and beta TCP, wollastonite, So these are all used for several orthopedic devices, orthopedic and dental devices, and many bony tissues, and also several bone matrix or those kind of solid application, which is very rugged means strong demanding applications it is used. And synthetic polymers also comes into picture. They are more controllable from the compositional and material processing viewpoint. And scaffolds architecture are widely recognized as important parameters when designing a scaffold. We have to take good care of the scaffold's architecture. Otherwise, it will not pass all these biological, physical, and chemical requirements. They may not be recognized by the cells due to the absence of biological signals, but you have to make sure that these scaffolds are not anti or against any biological signal. They should act neutral, so they don't favor or against. Sometimes for a given tissue they should favor, like we told that RGD, arginine glycyl aspartic acid, should allow the attachment of cells on them. So you have to include that tripeptide. Many natural polymers are used. Natural materials are readily recognized by the cells. Interaction between cells and biological ECM are catalyst to many critical functions in tissues. So natural polymers are quite friendly for these kind of biological reactions. So classification of polymeric biomaterials and scaffolds include, they are broadly into natural polymers and synthetic polymers. Natural polymers include silk fibroin, chitosan, starch, gelatin, alginate, cellulose, etc. Synthetic polymers include polyglycolic acid, PGA, polylactic acid, PLA, polycaprolactone, PCL, and polyvinyl alcohol, PVA, polymethyl methacrylate, PMMA. Some of these examples we discussed in the very beginning of the scaffold. I told you that we will see more in detail about them. So you may go back and revisit different morphology photos we had shown, and there some of them have come in that situation. So advances in scaffold technology, we need to know cell matrices for a 3D growth and tissue reconstruction. So any shape tissue you want to make it, you must have a suitable scaffold. We don't have a universal scaffold or one like a Swiss Army knife. You have one solution for all. It is not like that, because every tissue has got a different density, different functionality, different morphology, etc. Everything is different for different tissue. You don't want your kidney to be as solid as a bone, or not that you want your bone as liquid as a kidney or liver. So both are useless. So we should understand the material suitability also decided based on that. Biosensors, biomimetic and smart devices, they should have a unique properties. Like I mentioned about the heart valves, they should not cause any blood clotting or any inflammatory response in the heart tissue because of this valve being implanted. So these things has to be taken care of. Controlled drug delivery and targeted delivery. When you are putting some drug into the animal, we don't want, even while making this tissue, we don't want this scaffold block this entry of this drug or the exit or the any biological degraded material. You don't want the scaffold to block it. This all comes under the biocompatibility. And biohybrid organs and cell immunoisolation. So we want to be sure that the scaffold, while present in a living organism, it is non-existent. So that is the so-called biohybrid organs. When you make it, it will stay forever. So what are some of these challenges what we face? To more closely replicate complex tissue architecture and arrangement in vitro. That is one of the challenges. To better understand the extracellular and intracellular modulators of cell function. That is another challenge. To develop novel materials and processing techniques that are compatible with the biological interfaces, and to find better strategies for immune acceptance. So these are all some of the challenges that is faced by scaffold manufacturing or synthesis time. We will learn more about the regeneration biology and tissue engineering in the next class. Thank you.